today's topic is section 12.4 in your textbook, which is implicit differentiation. And it's really not that hard, so like I don't want you to be intimidated by implicit differentiation. If you know how to do your derivatives, then you should be like really good as far as today goes. And so there's like a little short 3-step procedure that you don't even really need to memorize. But if you want to find the derivative, dy dx, the derivative of y with respect to x, using implicit differentiation, you're going to want to basically look at your equation. There's going to be a right side and a left side. Take the derivative of both sides with respect to x. We're going to have to remember that y is our dependent variable and x is our independent variable. So we say like y is a function of x. We're not actually going to explicitly solve for y as a function of x, but we're just going to remember that. And so remembering that y is a function of x, there's going to be a certain application of the chain rule. And I'll point that out whenever we get there. And then once you take that derivative of both sides, you just have to now use algebra skills to just rearrange and solve for dy dx. We're just going to do a bunch of examples in practice today, like a lot. So hopefully you get this idea down pat with lots of examples. So this is just a reminder. This is stuff we learned earlier. But remember that your derivative, dy dx, is going to be the slope of a tangent line to the curve that describes your function as it appears in the xy plane. And if you want to make a circle in the xy plane, the right formula or the right equation for a circle is given here. This x squared plus y squared equals 1. That actually gives us a circle. So let me open up Desmos and let's put in x squared plus y squared equals 1. So that's a circle in the plane with radius 1. And maybe you're curious, maybe you're thinking, what would be the slope of a tangent line if I pick one point along the circle, one point along the red? What would be the slope of the tangent line to the circle at that point, right? We want to be able to calculate that. So since our derivative is the slope of the tangent line, what we're going to do is follow that procedure, that 1, 2, 3 procedure, and we're going to say, I'm going to take the derivative of the left side and the right side of this equation with respect to x. So on the left side, the derivative of x squared with respect to x is going to be what? 2x. And then this is the part that's new, or this is the part you haven't seen before, where we have y squared, and we remember that y is a function of x, so the y value depends on what your x value is. We're going to call this 2y, because we're like taking the derivative, sort of. But then we're also going to write dy dx next to it. And the reason we're multiplying by dy dx is because of the derivative chain rule. So the chain rule says first take the derivative of the outside function and then multiply times the derivative of the inside function. Well, in this case, the y squared is going to be like our outside function, and then the inside function is just y, because y is a function of x. And so the derivative of your inside function is actually, we write it dy dx to talk about the derivative of y with respect to x. And so this multiplying here is unfamiliar to you because you haven't done this before, but it's really just using the derivative chain rule and remembering that y is a function of x. And then on the right-hand side of the equation, that number 1, what's the derivative of 1 with respect to x? Nothing, yeah. The derivative of any constant is 0. So what we've done, going from this line to this line, this is what's called implicit differentiation. And so it's differentiation because that just refers to taking the derivative. Differentiation is just taking the derivative. And we say it's implicit because that first line, x squared plus y squared equals 1, is an implicit function of y, or it's y as a function of x, but it's given implicitly. Maybe you remember from algebra the difference between implicit and explicit. That explicit means you have y equals and then some function of just x. Implicit means that you have y sort of tangled up in the mess of the equation itself. So like where you have y squared over here on the left-hand side with some x's, that's implicit because you don't have y isolated by itself. So that's what we mean by implicit differentiation. And now step 3 in our little procedure, solve the remaining equation for dy dx. Now I just want to isolate this dy dx. And so I can subtract 2x from both sides and then divide both sides by 2y, and I get negative x over y for my derivative. When you subtract 2x from both sides and then divide both sides by 2y, you get negative x over y for your derivative. Now usually, whenever we finally take the derivative, we have the derivative as just a function of x, but in this case, we have the derivative as a function of x and y. And that should sort of make sense, because if you are looking at our circle, and you're asking what's the slope of a tangent line somewhere on this circle, well, you would actually need to know what the y value is, not just the x value. Because for any given x value, in between -1 and 1, there's actually 2 y values. And you have to tell me which y value you're talking about before I can tell you what the slope of the tangent line would be. If you were talking about this point on the circle, then your tangent line would have a negative slope. And of course, if you're talking about the same x value but a different y value down here, then your tangent line will have a positive slope at that point. So we can write an equation for a line like y minus some y value equals m times x minus some x value. This is just the point slope form of a line. And the slope of our tangent line is going to be negative x divided by y. That's what we just determined. But, you know, there's a way to lock that into the circle, and I can't remember how to do it. Maybe I need to do this. Does that work? No, that doesn't work. Let's try this. X 0, comma, y 0. Okay, cool. So this point, I can drag this point around, and it's going to be specifying the x and y that I'm using to calculate the slope of the line. So if I put this point on the circle, like this, then that makes it a tangent line automatically, right? Just the way I've calculated this. And so again, you have a tangent line to the circle up here, and it's got a negative slope, and you've got a tangent line to the circle down here, and it's got a positive slope. So you not only have to know the x value to get the tangent line, you would also have to know the y value, because your circle has, you know, 2 y values for every x value. All right, but that's sort of the motivation and the idea. Honestly, there's not a whole lot of like real world applications for implicit differentiation. This is one of the topics in class that's not quite as applicable as other things. But we're going to learn it anyways because it's in the book. It's good practice for derivatives in general. So let's do one more example. If I have x to the 4th plus y to the 4th equals 7, and I'm trying to find dy dx, we just take the derivative with respect to x of both sides, which is going to give me 4x cubed plus 4y y cubed. And then because of the derivative chain rule, and because y is a function of x, we're going to multiply times the derivative of y with respect to x, and then set that equal to the derivative of 7, which is 0. Thank you. Now if you want to solve for dy dx, you just subtract 4x cubed from both sides, and then divide both sides by 4y cubed, and you should get negative x cubed over y cubed. So if you've seen example 1, try practice number 1 on your own. I'll give you a couple minutes to attempt practice number 1 and see if you can calculate dy dx for that equation. Okay, so taking the derivative of the left side, derivative of x cubed is
3x squared.
3x squared. And then for y to the 5th power, what do I write?
5y to the 4th.
Yeah, 5y to the 4th
Times dy over dx.
times dy dx. Perfect. Okay. Equals what? 0, yeah. And then if we want to solve for dy dx, what do we get?
I got negative x squared over y to the 4th.
You're close.
3x squared over 5y to the 4th.
Yeah, exactly. So don't forget you're going to subtract 3x squared from both sides and then divide both sides by 5y to the 4th. It just so happened in our previous examples that the 4's canceled and the 2's canceled, but in this case they don't cancel out. Okay. So new example. We've got x squared times y to the 5th equals 5. So now if I'm trying to find, what is dy dx, that's what we're doing for all of these examples, by the way, is finding that. On the left-hand side of the equation, I'm not going to just need the power rule, I'm also going to need the product rule. So I'm looking at a product of two things, x squared times y to the 5th. And so my derivative product rule says that if I have some two functions multiplied together and I'm trying to take the derivative, this is going to be f prime g plus fg prime. And in my case, I could say that f is x squared and then g is y to the 5th. So that means f prime would be 2x and g prime is going to be 5 y to the fourth times dy dx. And so using this product rule over here, that makes the left-hand side f prime, which I write as 2x, times g, which is y to the fifth, plus f, which I write as x squared, times g prime, which I write as 5y to the fourth dy dx. And then for the right-hand side of my equation, what's the derivative of 5? 0. So rearranging this and solving for dy dx, I want to subtract 2x y to the fifth, so minus 2x y to the fifth on both sides. And then I want to divide both sides by x squared times 5 times y to the fourth. And this time I can simplify it a little bit more. I can write dy dx is equal to negative 2 over 5. In the numerator I have an x, and in the denominator I have an x squared. And so that leaves an x in the denominator. And in the numerator I have a y to the fifth. In the denominator I have a y to the fourth. So in the numerator that leaves a y. So just for my own curiosity, I wonder what this looks like if I map it in Desmos. So I do x squared y to the fifth. That's fine. So the red curve is x squared times y to the fifth. And the formula we got that should describe the slope of the tangent line was negative 2y over 5x. And so, in theory, when I move this dot onto the line, it should be the tangent line at that point. So, yep. Just further evidence that the derivative is the slope of the tangent line, and that this implicit differentiation stuff is working for a reason. It works out. Okay. So now try practice number 2 on your own.
How did you
Give you a few minutes.
How did you just get 5x at the bottom?
Okay. Are you okay up to this point?
Yes.
Okay. So I have an x in the numerator and an x squared in the denominator. So the x in the numerator and the x squared in the denominator, that's like x over x times x. So I can cancel 1, and I get 1 over x. So that's why it appears.
So same with the y? Okay.
Yep. Oh, by the way, Miguel, the blank packet has all these problems in it, so if you like your notebook better, that's fine too. I just wanted you to see it. Okay, so for this practice number 2, I'm again thinking product rule, because the left-hand side is x cubed times x to the 4th. So my f prime is going to look like 3x squared. And my g is going to be y to the 4th. And then I have plus fg prime, so it's going to be plus f is x cubed, and g prime is going to look like 4y cubed. So that's the left-hand side, and I can't forget my dy dx, because remembering that, the derivative chain rule says that inside function y is a function of x. I have to multiply times the derivative, so times dy dx. And then on the right-hand side, what's the...
0.
Yeah, the derivative of a constant is 0. Perfect. So now again, solving for dy dx, I have to subtract 3x squared y to the 4th from both sides to get rid of that term. So minus 3x squared y to the 4th. And then after that, I will want to divide by x cubed times 4y cubed. So dividing by x cubed times 4 times y cubed. And I can simplify this a little bit. This is still going to be negative 3 over 4. But now x squared divided by x cubed is going to leave just one x in the denominator. And y to the 4th divided by y cubed is going to leave just a y in the numerator. Okay. So new example. And it says 5 square root x is equal to 3 square root y plus 1. And before I start, I'm going to write this as 5x to the power 1/2 equals 3 y to the power 1/2 plus 1. Just remembering that the square root is the same as the 1/2 power. And now if I take the derivative of the left side, that means I bring down the 1/2 using, think about derivative power rule. I bring down the 1/2 and this becomes 5/2. And then I subtract 1 from the exponent. So this is going to be x to the power negative 1/2. On the right, same thing, I bring down that 1/2 and I get 3/2 y to the power negative 1/2 times dy dx. Don't forget the dy dx. Plus 1, that just goes to 0 in the derivative. And now, I'm going to remember that, again, the 1/2 exponent makes it a square root. If you have a negative in the exponent, that means you can move it to the denominator. So on the left-hand side, I'll have 5 over 2 square root x. So I put the square root x in the denominator because it's x to the negative 1/2 power. Equals 3 over 2 square root y. For the same reason, it's y to the negative 1/2 power times dy dx. And so since my ultimate goal is to get dy dx by itself, I want to multiply both sides of the equation by 2 square root y. So I'll get 5 times 2 times square root y, because I'm trying to get rid of that denominator. And then I'll divide both sides of this equation by 3. So in the denominator, I have 2 times 3 times square root x. And I can see these 2's are going to cancel. And so the simplified answer here is going to be 5 square root y over 3 root x. Any questions about that one? Go ahead and try practice number 3. Okay, so we're going to write this as 2y to the half power equals x to the half power minus 25. Now we're going to take the derivative of everything with respect to x. So this is going to be 1, because 2 times 1 half is 1. Y to the power negative half dy dx is equal to 1 half x to the negative half power, and then plus 0. So we've taken the derivative. I want to put it back into the square root notation. So I'll write 1 over square root y dy dx is going to be equal to 1 half times 1 over square root x. Now solving just for dy dx means I want to multiply both sides times square root y. And so it'll end up being square root y over 2 square root x. Questions? is way more fun for me than having to erase the whiteboard. Okay, let me show you example 4. In example 4, we have an exponential function. You have the e popping up here. So we'll jump straight into taking the derivatives. And so power rule says that that left-hand side should be 2 times 5 times x to the 1 power. So I'll write 10x. And on the right-hand side, the 1 goes to 0 in the derivative. And then the negative e to the y power
It's just
is
negative e to the y.
going to be negative e to the y times
Times dy over dx.
yeah, times dy dx. Yep. Because our derivative chain rule combined with the fact that y is a function of x means I have to multiply times the derivative of that inside function, which is just dy dx. So now I'm trying to solve for dy dx. I'll multiply both sides times a negative 1 just to get rid of that negative sign. And so I'll get negative 10x equals e to the y dy dx. And then I divide both sides by e to the power y. So I can write dy dx. That is going to be negative 10x divided by e to the power y. Let me know if you have any questions. Whenever you want, you can get started on practice number 4 down there. Yeah.
And negative e, actually like leave it to like negative 10. Just like divide by negative 1.
Sorry, what?
That negative e, actually it's like the negative 10.
Oh, you mean just in the first, line to the second line there? Yeah, I just multiplied by negative 1. Because like the negative e to the y power is just like negative 1 times e to the y power. So if you multiply by another negative 1, it'll get rid of it.
And since you did that, that's a little bit easier. So it's supposed to be e y over negative 10x.
So if we're going from this right here, I want to get dy dx by itself. So I need to divide by e to the y to cancel that e to the y. And so I divide negative 10x divided by e to the y. Well, I don't mean to rush you through this, and I'd like to give you more time for practice, but I want to make sure I get through all these examples before the end of class today. So I'm going to go ahead and jump into the solution for practice 4. So power rule on the left-hand side means I bring down the 2, and I can write 10y dy dx. And on the right-hand side, the 1 goes to 0 in the derivative, and then I have negative e to the x, which actually remains the same, right? The derivative of e to the x is just e to the x, And the negative 1 constant that you're multiplying by stays the same in the derivative as well. So now if you're trying to solve for dy dx, just divide both sides by 10y, and you get negative e to the x over 10y. Okay, so example 5. Again, we have an exponential function e to the y there, but we also have to deal with a product rule because we have this x times e to the y. So that means tells me I'm dealing with derivative product rule. So I'll just write it out for the first go at this. If I'm taking the derivative of product of functions like x times e to the y, this is going to be f prime g plus fg prime. My f is going to be, let's just say 2x. My g is going to be e to the power y. So f prime is just 2, and then g prime is going to be e to the power y dy dx. Now, that's the left-hand side after the derivative, so I just have to write f prime g. So I'll write 2 for f prime and then e to the y for g plus fg prime. So I write 2x for f and e to the y dy dx for g prime. The right-hand side of the equation is 15, so taking the derivative gives me 0. Now, if I want to solve for dy dx, I'm going to subtract 2ey from both sides. So I get minus 2ey. And then I'll want to divide both sides by 2x e to the y. So dividing by 2x e to the y. And then I can simplify that by saying the 2's cancel, numerator and denominator, and the e to the y's cancel, because I have the same thing in the numerator and denominator. And in the numerator, I'm left with a negative 1, and in the denominator, I'll be left with an x. So go ahead and try practice number 5 when you're ready. I'll give you a couple minutes for practice 5. So I started from this line, and then I said, well, I want to get dy dx by itself. And so I'm going to subtract this term, 2e to the y, from both sides. So if I subtract it from the left side, it'll cancel out. And then 0 minus 2e to the y is going to give me negative 2e to the y. And then once you have that, you say, I still want dy dx by itself, so now I need to divide by 2x e to the y. Get that 2x e to the y in the denominator.
Why don't you put right there my g prime? Why don't you put dy dx by itself? On this first two.
Right here. So if my g function is e to the power y, and we remember that y is a function of x, y is some function of x. The derivative chain rule tells us that we first take the derivative of the outside function, which e to the y would be our outside function, and the exponential is its own derivative, so we just write e to the y again. But then we have to multiply times the derivative of the inside function. And so our inside function now is the function y. And the derivative of y we write as dy dx. And so this dy dx pops out because of the chain rule and because y is a function of x. By the way, if you don't get something copied down into your notes, I'm going to post this on Canvas later, and so you can always get to it on Canvas, and you don't have to worry if you missed something as we're going by in class, because I know we're going a little bit quickly through this. So I'll show you the solution now for practice number 5. So on the left-hand side, I've got product rule, again, because I've got x cubed times e to the y. And so my product rule tells me f prime g, which I'll write as 3x squared e to the y, plus fg prime. So that'll be x cubed, and then g prime is going to be e to the y dy dx, is equal to a constant, so in the derivative, the constants go to 0. And then solving for dy dx, I have to subtract 3x squared e to the y from both sides. So to cancel that term, I subtract that. And then to cancel the x cubed e to the y, I have to divide by x cubed e to the y. And as I'm simplifying, the e to the y's cancel, and x squared cancels, and so I end up with negative 3 over x. That was actually very similar to the previous problem. Okay, so let me get purple. So new example, we're actually dealing with natural logarithms now. So that's another derivative we had to memorize before spring break. And on the left-hand side, if I take the derivative with respect to x, the 3 stays there. And does anybody remember what's the derivative of natural log? 1 over x. Awesome. So this is going to be 3 times 1 over x. On the right-hand side, the 5 goes to 0. I keep the negative. And we just talked about how the derivative of natural log was 1 over y in this case. But also, I have to multiply times the derivative of my inside function, where my inside function is the function y, so I write the derivative as dy dx. I'm trying to solve for dy dx now. So I'll multiply both sides times negative 1 and get negative 3 times 1 over x is equal to 1 over y dy dx. And now, if I want to get rid of that 1 over y, I need to multiply both sides of the equation by y. So I'll get negative 3 y over x is equal to dy dx. Go ahead and try practice number 6 when you're ready. Okay, I'm going to show you the solution to practice 6 so we can move on. This is going to become 2 times 1 over y. And so, yeah, good job remembering. I almost forgot it. Times dy dx. And then on the right-hand side, power rule says I bring down that 5, and 7 times 5 is 35, x to the 4th, and then the plus 6 goes to 0. So trying to solve for dy dx now. I'm going to divide both sides by 2 and end up with 35 over 2, and then multiply both sides times y, so I end up with something like that. 35 halves, x to the 4th times y. Okay, example 7. Has 8 times y times natural log x equals 14. So I see a product of two things on the left-hand side. The product rule being this, f prime g plus fg prime, where my f function is now going to be 8y. My g function is natural log of x. That means f prime is going to be 8 times dy dx. Because the derivative using power rule of 8y would just be y, so it would just be 8. But then remember, you have to multiply times dy dx, because the derivative of y is really dy dx. Okay. G prime is
1 over x.
1 over x. Thank you. Cool. So going back over here, my left-hand side is going to be f prime g, which is 8 dy dx times natural log x, plus fg prime, which is 8y 1 over x. On the right-hand side, 14 goes to 0 in the derivative, so this is what we're looking at, and I'm trying to get dy dx by itself. So I have dy dx over here times 8 times natural log x. And then I'll go ahead and subtract 8y 1 over x from both sides. And so on the right-hand side, I get negative 8 y over x. Then, to get dy dx by itself, I want to divide by 8 natural log x. And so I have negative 8 y over 8 natural log x times x. And then the 8's cancel. And so the simplified version of this is going to be negative y over natural log x times x. And that's probably, well, I say it's probably the trickiest example. Practice number 7 adds maybe a little bit more trickery to it. So I'll give you a few minutes, maybe 3 minutes to work on practice number 7 before we move on. product rule? Or
Usually always go with the y's, right? The y's, just a regular one.
yeah, so and maybe this is important to say, but if you tried to do the same thing with your x's, right? Like so we in g prime over here, we just took the derivative of natural log of x is 1 over x. If I then multiplied by the derivative of x with respect to x, well, dx over dx, that's just 1, and multiplying by 1 doesn't really do anything, and so that would cancel itself out. Right? So it only really matters when you have y terms involved, right? So again, when we say f prime, we're saying that's the derivative of 8y. And so when you have a constant multiplier like h out in front, that stays the same when you take the derivative. You don't change that 8. But when we were asking what is the derivative of y, well, the derivative of y is dy dx. That's how we write the derivative of y with respect to x. So that's why that pops up. Trust me, I definitely know that this is tricky. It's something that requires a lot of practice, and we don't have a whole lot of time in like a college class to get that practice in. You know, the way, like whenever I taught high school, it was like we had an hour a day, 5 days a week for something like 36 weeks. Yeah, 36 weeks a year. And so that's a huge number of hours to like spend in class working on stuff. And then when you get to a college level course, you have a little bit less than an hour and a half, 2 times a week, so 3 hours a week for only 16 weeks. So that's only like 48 hours total. You have way fewer hours to spend in class here. And that's why it's so important to like get practice outside of class, is because a lot of students who are really successful in high school just by showing up to class and paying attention find that they're not successful in college just because you don't end up spending the same number of hours learning the material. So time spent practicing is the most important thing. On number 7, practice number 7, we have the same sort of product rule situation going on the left-hand side. So I have to write f prime g, where f is going to be 7y squared, and g is going to be natural log x. So f prime is going to be like this, 14y dy dx, times g, which is natural log x, plus fg prime is 7y squared. G prime is going to be 1 over x, and then the 3 goes to 0 when I take the derivative. Now, I'm trying to get dy dx by itself. So I'll first subtract that 7y squared over x from both sides. So bringing it over here, I'll write 14y dy dx natural log x is equal to now a negative 7y squared over x. Again, trying to get dy dx by itself, I want to divide by 14, I want to divide by y, and I want to divide by natural log x. And so my numerator over here is going to stay the same. And then now, in my denominator, I have that x, but I also have 14, I have y, and I have natural log x, all added to my denominator here. I can simplify just a little bit because 7 over 14 is 1/2. And I have 2 y's in my numerator, y squared, and I have 1 y in my denominator, and so that's just going to leave 1 y in my numerator and no y's in my denominator. So my new denominator should be 2x natural log x. And there's your answer. Okay, so jumping into our word problems. let's say you're managing a hotel and you have developed this math model that predicts the demand for rooms as a function of price. And so the way that price and demand works is that if you raise the price of something, the demand goes down, right? If you're charging an excessive price for something, people don't want to buy it. Whereas if you lower the price, demand goes up because people always love a sale. People like to get a good value on things, and so people are more likely to buy if the price is lower. That should be what we're observing here, is that the price, as the demand goes up, the price would go down. So that's the correct relationship here. And our question says, use implicit differentiation to find the rate of change. And by the way, rate of change, remember, just means we're going to be finding the derivative. The rate of change in demand with respect to price whenever n is equal to 5. So the way that you would write the rate of change in demand with respect to price is this, the derivative of n with respect to p. Because we're saying demand is n and price is p for this equation. So what we're trying to find is dn dp. And we're told we're supposed to use implicit differentiation. So now that we've figured out what we're trying to do, we will take the derivative with respect to p of both sides of my equation, because I'm trying to get dn dp. The derivative of p with respect to p is what? What's the derivative of p with respect to p?
2n.
It's going to be 1 for the left side of the equation, right? If you're doing p and just taking the derivative, that gives you 1. On the right-hand side, 5,000 goes to
constant, so that's 0.
0. Perfect. Thank you, Cyrus. And then this negative 2n over 20, there's a constant multiplier, negative 1 over 20, multiplying n squared, right? This little bit, I could rewrite it as negative 1 over 20 times n squared. And then the derivative of n squared is just 2n. And so now I write times 2n. So I also, right here, need to remember something. What am I forgetting to do? dn dp. Yeah, so derivative chain rule tells me I have to multiply times the derivative of the inside function. And when we're asking about the rate of change in demand with respect to price, we're acknowledging that demand is a function of price. In other words, demand depends on price. As price changes, so will demand. And so we write dn dp over here. Okay, so I see a 2 divided by 20. I could write that as 1/10. This is 1 equals 1 over 10 n dn dp. And I'm trying to get dn dp by itself, so maybe I'll multiply both sides by a negative 10. And multiplying both sides by negative 10 gives me negative 10 equals n dn dp. And then I'll divide both sides by n, and I get negative 10 divided by n equals dn dp. So this is almost the answer. But if you look back at our question, it wants to know what is the rate of change in demand with respect to price whenever n is equal to 5. And so to calculate dn dp when n is equal to 5, this will just be negative 10 over 5, which is going to be negative 2. And so my answer is going to be negative 2 for this question. So for every dollar that you change the price, the demand is going to change by 2 hotel rooms. If you increase the price by $1, that's 2 fewer hotel rooms that you're going to book. If you decrease the price by $1, that's 2 more hotel rooms that you're going to book. And that only applies really whenever the current demand is 5 rooms. If you had a different demand to start out with, then you're going to have a different rate, you're going to have a different dndp relationship, because we just found that dndp depends on what that value of n is. Okay. Let me see how many more problems we have, because we only have 10 minutes of class, and I want to make sure I get through all these. Okay, we have 3 more problems in only 10 minutes, and so I'm not going to give you a chance to work these on your own. I'm going to go ahead and just show you the solutions to these examples. This says a food truck owner has developed a math model where he predicts the demand for burritos as a function of price. So again, if you raise the price of a burrito, fewer people want to go to your food truck to buy those burritos because maybe they're overpriced. We want to find the rate of change in demand with respect to price, and we already talked about the rate of change of demand with respect to price is written dndp, and this time we want to find it when n is equal to 30. So if he has every day 30 people coming to buy burritos, and he wants to know how much will that demand change if I change the price of a burrito, this is the sort of question that we're asking. Very business applicable question. So if I want to find the derivative of n with respect to p, I'm going to take this whole equation and take the derivative with respect to p of both sides. So 10p in the derivative goes to 10. 300n squared is going to go to 300 times 2n times dn dp. And then 75 goes to 0. So solving for dndp now, I want to subtract 10 from both sides. Subtracting 10 from both sides gives me negative 10. And then I want to divide both sides by 600n. And so I can cancel a 0 and get negative 1 over 60n. That's my formula. Again, to point out, I'm actually concerned about when n is equal to 30. So if n is equal to 30, then dndp at n equals 30 is going to be negative 1 over 60 times 30, which is going to be negative 1 over 1800. Sorry, that's a hard color to read. Let me fix. Negative 1 over 1800 should be your solution to this question. Which is really, 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 really tiny. So he's saying that, you know, if he changes the price of a burrito by $1, only one tiny fraction of a customer will change, right? Like over the course of 1,800 days, maybe you expect one fewer customer to come buy a burrito. So this is not very real life accurate. It doesn't really describe reality that well, but again, these are the kind of questions that you could answer with derivatives and the same process. It's just unfortunate that one didn't have an answer that made sense. Here we go. At a given company, the math model that describes the relationship between revenue, capital R, and the number of full-time employees, N, is given by this. And so I guess maybe this pops up if you're like a consultant and you're looking at companies and you're looking at their revenue and the number of employees. You say, well, it tends to follow this relationship. And you might look for companies that are outliers and try to coach them to get them to be more efficient somehow. So we're going to use implicit differentiation to find the rate of change in the number of employees with respect to revenue when this is true. But the number of employees is N and revenue is R, so the rate of change, being the derivative, is going to be dN dr. That's what we're looking for. So taking this and then taking the derivative with respect to capital R, the left-hand side is going to be 2,000 times 2r, and you could write times dr, but that's just times 1, so that doesn't matter. On the right-hand side, we'll have 3n squared times dn dr. And so again, finding dn dr is now just a matter of algebra. where I want to, probably first recognize that this is 4,000 R on the left-hand side, 3n squared d and dr on the right. And then divide both sides by 3 and divide both sides by n squared. So this is 4,000 R divided by 3n squared is equal to this d and dr that I want to know. But we're concerned about this. When revenue is 128 and number of employees is 320, that will be 4,000 times 128 over 3 times 320 squared. Now, on an exam, you will have a calculator handy. And for me right now, I just don't feel like working this out, but you can see that this is some numbers divided by some other numbers, and you could figure that out if you had a calculator. And so for right now, that's going to remain a mystery, unless you happen to have a calculator. All right, 4 more minutes. So we're going to work this one super fast. The concentration of a certain pain medication that remains in your blood after T hours can be approximated by this. So Y is the concentration of pain medicine, concentration of aspirin or whatever you're using. And T is the number of hours after you take the tablet. So we're going to use implicit differentiation to find the rate of change in concentration over time. So the rate of change in concentration over time looks like this. The lowercase d means change in, so we're talking about change in concentration divided by change in time. And this is what we want to know. So starting here and taking the derivative with respect to t of both sides, on the left-hand side, this is a product of y times e to the power 1/5 t. 0.2 is just 1/5, and so I might write it as 1/5 t. So product rule, derivative product rule, is going to tell me first we're going to do f prime g, which means I'm going to write dy dt for f prime. And then g is e to the 1/5 t, so write e to the 1/5 t, plus f g prime, and g prime is going to be 1/5 e to the 1/5 t. On the right-hand side, 99 goes to 0 when I take the derivative. And now I'm just trying to solve for dy dt. So I can write dy dt is equal to, subtracting this term from both sides gives me negative y 1/5 e to the 1/5 t. And then I want to divide both sides by e to the 1/5 t to get rid of this factor over here next to the dy dt. And I'll notice that these e to the 1/5 t's cancel. So that means that dy dt is going to be equal to negative y times 1/5, or negative y over 5. We are now asked the question, what about when the concentration is 9? And so if our concentration is 9, then the rate of change in concentration over time is going to be negative 9/5. That's how you'd find that answer.